Hi, welcome back. So this is second lecture of the course Bayesian modeling, and so in the last lecture we have covered some basic operations that we can do on sets, and that would be a very useful background for introducing you to more important concepts like probability and random variables, which would become very useful later on in this course. All right, so keeping in mind whatever you have covered in the sets, you can practice them a bit. So I'm assuming that now you can do some basic operations like union of sets and intersection of sets, and you can calculate power set of any set. So assuming that background, we're starting with an example. All right, so consider this, that you are doing an experiment where the participant sees a string on the screen, okay, and this string could be either a meaningful word or a meaningless string which does not make any sense. So let's say this string could be either, let's say, book, or it can also be something like BKTR, which does not make sense, right? Now the task of the participant in this experiment is to recognize whether this string is a meaningful word in English or not. Okay, so they need to press a key if it is a meaningful word, and if it is not a word, then they press some another key. So it could be left or right key. Okay, so what we are recording is that whether they are producing a yes response or a no response. So let's say a participant sees book on the screen, so they would make either a yes response or a no response. So in this case, for example, most participants would make a yes response, but sometimes it can happen that they confuse it with some other non-word and they make a no response. Okay, and same here as well. Okay, so what we are recording in this experiment is their response, which could be either yes or no. Okay, for any such experiment and for any survey that you do on web or any kind of questionnaire, what you can always define for your experiment is something called a sample space. So you can define the sample space of your experiment for any experiment. In this case, it's an experiment where you are recording whether it's a proper meaningful word or not. Okay, so sample space of an experiment is the set of all possible outcomes. Okay, so in this case, what are the possible outcomes of this experiment? There are two possible outcomes here. One is a yes, okay, and another possible outcome is no. So these are the two possible outcomes of this experiment. So a set containing all the possible outcomes is called the sample space of the experiment, and we denote it using this symbol omega. Okay, so sample space is a set containing all possible outcomes of your experiment. Okay, so each experiment would have a sample space. Okay, so for example, let's say you're tossing a coin. Let's say in a coin toss, what are the possible outcomes when you toss a coin one time? There are two possible outcomes. It's either head or tails. So this is your sample space for a coin toss experiment, a set containing heads and tails. For this particular experiment, where you're recording whether they respond with a yes or no, your sample space is a set containing yes and no. You can write them inside inverted comma. That's better. Okay, so this is one thing you can define for any experiment. You can define a sample space. Now another thing you can think of is this, that what are all the possible subsets of this sample space? Okay, so what are all the possible subsets of the sample space? So let us think, what are all the possible subsets? Let us consider a set containing only yes. Is it a possible subset of this sample space? Yes, it is. Another set containing only no. It is also a subset of omega. A set containing both yes and no. It is also a subset of omega, right? And also you can think of an empty set, which is also a subset of omega. Okay. So essentially what we are saying is that you can figure out a power set of omega. Remember the power set? What is a power set? It's a set of all the possible subsets, right? So power set of omega would be the set of all possible subsets of omega. So this would include a set containing only yes, a set containing only no, a set containing yes and no, and an empty set. Okay. So this is the power set of omega. Now the power set of the sample space is called event space of the experiment. We call it the event space, and each member of the event space is called an event. We call them events. So you can call them, let's say this is event E1, this is event E2, this is event E3, and this is event E4. So there are 4 possible events in this experiment: yes, no, and phi. Okay. So notice that I'm making a distinction between an outcome and an event. Yes and no are outcomes. Okay. A set containing all the possible outcomes is the sample space. Now event space is the power set of your sample space, and each member of your event space is called an event. Now why all this useful? Why we are talking about this? Because probability is all about events, and let me show you how. So probability is a way of assigning a real value to each event in your event space. Okay. So let me quickly rewrite our sample space and event space. So for the word recognition experiment, our sample space was a set containing yes and no. Okay. I can represent using yn, so that would be better. And the event space, let us represent event space by f, which is the power set of your sample space is a set containing yes, no, and an empty set. So these are all the possible events. Okay. This is E1, this is E2, this is E3, this is E4. Now probability is a way of assigning real values to each event in the event space. So you would assign them some real values, let's say V1, V2, V3, V4, based on certain restrictions. So let's say you figure out a way, let's say some function which assigns these real values to each event in the event space based on, constrained by certain restrictions. Okay. That's how we define probability. So probability is a way of assigning real values to each event in the event space constrained by certain restrictions, and those restrictions will define what real values we can assign to these events, because you cannot randomly assign any real value. They must be constrained by certain properties, right? And those properties comes from 3 axioms of probability, and those properties are fundamental to how we see probability. Okay. So those are called 3 axioms of probability, and we will take a look at 3 axioms. Okay. But before going into what are the constraints that we use for defining these probability values, we need to understand a bit more that why do we need this system? Why are we assigning these real values to events in your event space? Okay. So the idea is this. Recall our the original assumption that we started with, that if you are observing something in an experiment, let's say you are observing some data in an experiment, this data must be coming from some true generative process. Okay. The data must be coming from some true generative process, but we don't know what is that true generative process. Okay. We can only infer some properties of the true generative process by looking at the observations. But how do we do that? what we do is that we make an assumption that true generative process is actually a probability assigner function, let's say f of theta. You can assume some other function as well, some other kind of probability assigner function as well, but let's say you assume that true generative process is a probability assigner function f of theta. Okay, and what this function does, this function assigns real values to events in the event space of your experiment. Okay, let's say these are the events E1, E2, E3, E4. It assigns real values V1, V2, V3, V4. Why? These values would imply that which event would be more likely to occur in this experiment, which event would be less likely to occur this in experiment. So for example, if you repeat this experiment, when you do this particular experiment, which event would be more likely to occur and which event would be less likely to occur. So that's one interpretation of what these probability values are. Okay, so this is the basic idea, that we do not know what is the true generative process. We make some assumptions that what this true generative process could be, and the assumption we make is an assumption of a probability assigner function. We assume that this true generative process is some probability assigner function which assigns probability values, real values, to our events in this event space. And this function, this probability assigner function, must be constrained by three axioms that we will see, three axioms of probability. Okay. So what do we need the concept of probability for? Because it's how we define the fundamental assumption about the true generative process, because we think that the true generative process is a probability assigner function. This is the way it works, that it assigns some real values to each event in the event space, which determines whether which events would be more likely to occur when you repeat that experiment. Okay. So once we get data, so how do we make inference? So once we get data, using that data, we try to infer the properties of this probability assigner function. So for example, what would be the value of theta based on which this assigner function can assign probabilities to this, seeing this data. So what function can generate the data that you are seeing? Okay, so using the data, you try to infer the properties of this probability assigner function, and by extension, you try to infer the properties of the true generative process. Okay. So that's the basic idea, but the process of inference is not complete here. It goes one step further as well, but we will come back to that later. This is just for understanding that what is the role of probability in statistical inference, right? Because this is our fundamental assumption. This is what we think about the true generative process. The true generative process is a probability assigner function. It assigns some real values to events in your event space, which would determine which event would be more likely, which event would be less likely. So when we are trying to infer the true generative process, what we are trying to infer is the actual true probability assigner function that is behind your data. All right. So before further going into what could be this probability assigner function, we need to understand these three axioms, because three axioms are fundamental to defining what would be the nature of these probability assigner functions. Okay. So let us dive into what are the three axioms of probability. All right. So let us say this is your sample space omega, and this is your event space f, and your event space contains events like, say, E1, E2, and so on, right? So they belong to your event space f. Okay. The first axiom says that for an event E which belongs to your event space f, right? So probability of an event E is greater than equal to 0. Okay. So, probability of an event E is greater than equal to 0. So, probabilities cannot be negative. So, that is the first axiom. It is a simple and straightforward one. So, whatever probability assigner function you would have, it has to follow this restriction that it cannot assign a probability which is negative. Now, second axiom. The second axiom says that one of the elementary events must occur. Okay, one of the elementary events must occur. What is an elementary event? Well, elementary event is an event which contains only one member. Okay, recall our example where our sample space was yes, no, and our event space was yes, no. So, these were the events, event containing both yes and no and an empty set, right. So, these events E1 and E2, they contain exactly one member. Okay. These are called elementary events. Okay. These are called elementary events. So, second axiom says that one of the elementary events must occur. Okay. So, what does that mean? Well, if you have, let us say, elementary events E1, E2, E3 and so on in your event space, let us say all these are elementary events, okay, then one of them must occur. That means that the probability that at least one of them occurs should be equal to 1. So, the probability of at least one of them occurs should be equal to 1. How do we write this statement using a set? So, we want to write a set which provides you that at least one of the event occurs. Okay. So, the way to write this is union of these elementary events. So, it means the same thing. When I say that at least the probability that at least one of the elementary event occurs is equal to 1 means that probability of the union of all these elementary events is equal to 1. That is what it means. That either this occurs or this occurs or this occurs, right? It does not matter when you are taking union, okay, and all these are, by the way, they do not share any common element, right. So, when I am taking their union, what I mean is that either of them can occur, okay, and that probability is equal to 1, right. All right. So, this statement ensures that at least one of the elementary event occurs, okay. So, one of the elementary event must occur. But can you tell me what is the union of all these elementary events? E1, E2, E3. Okay? You can think of it in terms of what would happen if you take a union of all the elementary events in your event space. Well, it turns out that the union of all the elementary events is your sample space. So, what second axiom implies is that probability of your sample space is equal to 1. Although this statement could be more vague than this one. So, I would suggest that always remember this one, that the probability of union of your elementary event is equal to 1, that one of the elementary events must occur. So, this is more useful statement that would help you. So, this is your second axiom. Okay. Now, let us discuss the third axiom. The third axiom says that if you have mutually exclusive events, okay. What do I mean by mutually exclusive events? So, the events whose intersection is an empty set. So, let us say you have mutually exclusive events E1, E2, E3, so on, such that E1 intersection E2, if you take intersection of any two sets, okay, then the intersection is an empty set. If you take E1 intersection E3, then it is an empty set. Okay. Similarly, if you take E2 intersection E3, then it's an empty set. So, if you take intersection of any of these two sets, it's an empty set. Okay. So, none of these sets have a common element. Okay. So, if you have mutually exclusive events E1 to let us say En, okay, then the probability, so if this is true, if they are mutually exclusive, then the probability of the intersection of these mutually exclusive events is given by summation of their individual probabilities. Right? So, probability of intersection of mutually exclusive events is the summation of their individual probabilities. So, that is the third axiom. Okay. So, let us do one exercise. Let us apply these three axioms to our example of word recognition experiment, where a participant produces either a yes response or a no response. So, let us see what happens when we apply this to our word recognition experiment. Okay. So, what was the sample space? Sample space was yes, no, and event space was event containing yes, just no, both yes, no, and an empty set. And let us name them. Let us say this is E1, this is event E2, this is event E3, and this is E4. Okay. So, first axiom says that probability of any of these events is greater than or equal to 0. So, this would apply to any of these events. Let us say E1 is greater than or equal to 0. Similarly, probability of E2 is greater than or equal to 0. Fine. So, that is based on first axiom. Now, what does the second axiom say? That one of the elementary events must occur, that the probability of union of elementary events is equal to 1. So, what are the elementary events here? E1 and E2, event containing just yes and just no. So, E1 and E2 are the elementary events here. So, that means according to second axiom, probability of E1 union E2, so that is probability of yes union no. Okay. This is equal to 1. So, that is what the second axiom says. Okay. Now, let us go to third axiom. Third axiom says that if two events are mutually exclusive, that means events that do not share any common element, then the probability of their intersection is equal to summation of their individual probabilities. So, which events here are mutually exclusive in your event space? Are E1 and E3 mutually exclusive? No, right? Because they share a common element. Why? Are E1 and E2 mutually exclusive? Yes, they do not share any common element, right? So, the mutually exclusive events here are E1 and E2. Okay. So, let us focus on them. So, because if you take intersection of E1, E2, you get an empty set. That is why this principle would apply, that probability of E1 intersection E2, okay, would be equal to, oh sorry, so I made a mistake here, it is not E1 intersection E2, pardon me. So, in the third axiom, it is the not intersection, but the union. So, if events are mutually exclusive, then probability of union of these events is equal to summation of their individual probabilities. Okay. So, that is what applies, not the probability of their intersections, but probability of their unions. Okay. So, what it implies here is that if E1 intersection E2 is an empty set, then probability of E1 union E2 is equals to probability of E1 plus probability of E2. Okay. So, this is what we get based on third axiom. Now, interestingly, second axiom says that probability of E1 union E2 is equal to 1, and the third axiom says that probability of E1 union E2 equals to probability of E1 plus probability of E2. So, what we get is this from equations 2 and 3, that probability of E1 plus probability of E2, this is RHS of equation 3, is equal to 1. Okay. So, what does it mean? That there are two elementary events E1 and E2 in your event space. What it means is that whatever probability assigner function that you would assume for this process, remember this is the data that we will get in a word recognition experiment, yes no data, it would be generated by some generative process, let's say some cognitive process. Okay, that generative process is a probability assigner function, right? That's our fundamental assumption that we make. Now that probability assigner function must satisfy this constraint. And what is this constraint? That it assigns probabilities in such a way, probability values in such a way, that summation of probability of E1 plus probability of E2, the probability of E1 plus probability of E2 is equal to 1. Okay. So, whatever probabilities it assigns to the elementary events, summation of those probabilities is equal to 1. So, that is the constraint the probability assigner function must satisfy. So, what we have seen is that what are the three axioms of probability that defines what would be the constraints on the probability assigner function. Okay. And we have derived it for a very simple example where the possible outcomes are yes and no. And what we see is that that the probability assigner function should be such that the probability of the summation of probability of elementary events. So, here probability of E1 and probability of E2, their summation should be equal to 1. Okay. So, that is the first thing that we have figured out, that given any data or let us say any experiment where the possible outcomes are yes and no, or whatever possible outcomes you have, it could be any experiment, it would be generated by some true generative process. Okay. Now, we cannot directly infer, we cannot directly know what is this true generative process, we can only make some inference using the data. Okay. And how do we make inference? We assume that there is some probability assigner function which has generated this data. And how it generates the data? Well, what this function does, that it assigns some real values to all the events in your event space. Okay. Real values, let us say V1, V2, V3, these real values are called probabilities. So, this probability assigner function assigns real values to events in your event space, but this real value assignment must be constrained by three axioms of probability, and that we just saw. Okay, and we derived what those axioms would mean for this particular example. Okay. So, now what we need to figure out is the nature of this probability assigner function. We already know the constraints. So, what constraints it should follow. Now, we need to figure out that what kind of function can assign probability values constrained by these axioms. So, we will see some examples of these probability assigner functions for different cases. Okay. All right. So, that is it for this lecture. In the next lecture, we will see more about what kind of probability assigner functions we can define for these simple cases. All right. Thank you.